All right, recall from last video, if we're doing a power series, we can get three different types of answers. One is that it's going to converge for all x. That's where this series part here is going to take you to 0, and so it doesn't matter what value of x is you're going to get. We also have a series that would converge only at x equals 0. That's when our a sub n term is going to infinity, meaning the only way that this is going to be convergent is if that x value is in fact 0. And then what we'll end up probably getting most of the time here is that you will get a radius of convergence where it is only going to converge in some symmetrical interval around that radius, and that's where your series is going to leave you something where it's less than 1, and then you solve with whatever that power series comes out to be for that interval. Let's take a look at a real life example here of one. Power series are a way to represent some of the most important functions that arise in math, physics, and chemistry. In particular, the sum of power series in the next example is called a Bessel function after the German astronomer Friedrich Bessel. The function given in this next one is a Bessel function. In fact, these functions first arose when Bessel solved Kepler's equation for planetary motion. Since that time, they've used it in other physical situations, including temperature distribution in a circular plate and the shape of a vibrating drum head. And that's what this picture kind of looks like down here. It kind of looks like a drum head if you did it in slow motion, where the impact hit maybe right there, and it would vibrate from that point outward. So this next one would give a power series representation of that. That Bessel function of order 0 is given by this function here. So you can see it's a series that includes an x value there. So we know it's a power one because we got x involved. We also have some other stuff going on there too. Where does this converge? Well, good thing we see that there is an alternating part in here, but remember we always, with our two tests, our root test and ratio test, when we take the absolute value of this, that's going to get rid of that, so we're okay there. Now we got to decide, should we use root or ratio? Well, I see some powers of n that would be good to use root. However, we do have in here this factorial, which does not lend itself to root test. So we're going to want to use in this one our ratio test. So let's look at writing this out. So we want to do limit as n goes to infinity of the absolute value of these two, the bottom one being just our regular series here. So -1 to the n, x to the 2n, and this should have absolute, well, I guess it's all an absolute value. So I'll just go back here. And on top, with the ratio test, you want to do the +1. So here we want +1 on everything. So it'd be -1 to the n plus 1. This is going to be x to the 2 n plus 1. On bottom here, we got 2 to the 2 n plus 1. And this will be n plus 1 factorial, all being squared here. All right, so what can we simplify on this one? Well, a couple things. We know if we're taking the absolute value of this, that our terms here that have the negative, those are just going to be 1 when we do this. So we don't need to worry about those. Our x, though, does need to keep the absolute value around it. So we want to make sure that we continue to take the absolute value there. So let's try simplifying it. So our top numerator here is going to end up being x. And then if I distribute here, this ends up being 2n plus 2. On the bottom, I'm also going to distribute, so that'd be 2 to the 2n plus 2. And then this is n plus 1 factorial squared, meaning almost like we got 2 n plus 1 factorials here going on. I'm going to write it out as 2 since it's squared. All right, on the bottom of that, our alternating term there is going to go to 1 again. We got absolute value of 2 to the n over 2 to the 2n, and we got n factorial squared. So that just means really here we're going to have an n factorial and another n factorial. Let's multiply by reciprocal now. So I'm going to multiply by that denominator to get it into one fraction here. So if we do that, now this is going to end up being this. I'm going to, in this case, write this out as, if we got this to the 2n plus 2, I can write this as x to the 2n times x squared would be another way, because if we combine that together, we would add the exponents. Multiplying by reciprocal, this term would go to the numerator. And same with these two n factorials. Over, I'm also going to use that separating thing on this. So this would be 2 to the 2n times 2 to the first, or 2 squared, sorry. And then I got these n plus 1 factorials that I'm going to write as n plus 1 n factorial and another n plus 1 n factorial. And then also multiplying by the reciprocal, I would have our term here of this. All right, so now what is going to cancel out here? Our n factorials should cancel. Our x to the 2n is going to cancel. 2 to the 2n is going to cancel. And that looks like everything that cancels out here. So what do we have remaining now in our limit? That should simplify it a lot here. So we still have absolute value of x squared. On bottom there, 2 squared is going to be 4 to the n plus 1. Another way I could write that if I wanted would be, I'm going to move the absolute value squared over here. So then we would have the fraction of 1 over 4n plus 4. So as we go to infinity, what do we know about this? That's going to go to 0. And so if that's 0, 0 times whatever this is just going to equal 0, which is always going to be less than 1, which we want for ratio test. And so because of this, this particular one here, this Bessel function is going to be convergent for all x. It does not matter in this case what x is, because if we times it by 0, we're going to be always, it's going to be 0, which is always less than 1, so it's convergent for all x. Or recall from a previous video, we could also write that as x is going to be this our x is in the group of negative infinity to infinity, so all numbers.